Hi, today we are going to take a look at this interface fuel flow. This thing was manufactured by Foxtronic Incorporated, Dallas, Texas. On that side there is a sub-D25 connector. We can see two electronic boards. On this one there is a microprocessor, NSC800. It is from the family of Z80, Z80 if you prefer. There is a peripheral IC here, NSC810. There is an EEPROM which contains the code, 8 kilobytes. Here there is a timer, 555. I cannot read this part because of the conformal coating. This part is a voltage regulator, LM311K. We have here the power supply. And we have here a TVS diode, a few passive parts, and an LM10. You can see that the soldering is not the best. That code is 95 for this IC. We have a capacitor here from Jamicon. Here we have several resistor arrays, 100K. Here we have two LM224. So I guess there are something equivalent to an LM124 quad op amp, another resistor array. This is a transistor. Oh, it's an AD581. This is the voltage reference. We can see that we have only commercial parts except this one. We can see the low-cost resistors, carbon film. Here we have an LF12509. This is probably an analog multiplexer 128-509, or maybe a differential one, a dual 4-to-1. Here we have 3 op amps and also 3 transistors and 3 capacitors. So it seems that we have 3 identical circuits. So we can see these transistors have 4 pins. So this is probably a JFET transistor. Let's see if I can read the reference. Oh yes, it's a 2N4117A. It is actually a JFET with very low gate current. It is sometimes used as a diode. It is called a PAD, picoamp diode. So the thing that the input current is below 1 picoamp at 25 degrees, of course. And we can see also we have a guarding track here. And we have maybe 3 sample and holds here, or maybe integrators. This is a dual comparator. Here we have a 4046. This is a PLL. And we have here a dual D flip-flop. We have a multiplexer 4052. It's a dual analog multiplexer 1 to 4. Another analog multiplexer, so this is a triple multiplexer, 1 input, 2 outputs, or vice versa if you want. It is very difficult to read, but it seems that we have here an HCT 175, and we have a CA 2420. This should be a dual op amp, maybe CMOS input. We can see another JFET here, 4117A. I think I forgot these 2 parts. MUX 08 from Analog Devices. So obviously a multiplexer, maybe 1 to 8. The thing was not expensive to produce. We have more or less only commercial parts inside. And also there is no seed screen. Low-cost avionics. The manufacturing also was not the best. And there is no solder mask also. I think that we have a thin conformal coating. There is probably one, but very, very, very thin. This is a test setup for this fuel flow interface. This unit has 4 identical channels. I will test only one, of course. The input of that system is a synchro or a magnesin. So therefore, this unit is a quad synchro to DC converter or magnesin to DC converter. I have tried first using a synchro, but actually it was very unstable and very not linear. Therefore, I have used a magnesin. You can see here, it is the only one I have. It is something which is very difficult to find. The signals are more or less the same than the synchro. The difference is the frequency of the signals. The magnesin works with the second harmonic, so therefore we have signals at 800 Hz. I have connected this real indicator at the output of that unit. The range of this one is 0 to 5 volts. Let's turn on the power supply. We can see that this thing works. We can see also the acceleration of the scale here. We can see here the characteristic. We have here the angle of the magnesin transmitter from 0 to 350 degrees here. And here we have the DC voltage. We can see that we have two different slopes. One here and a second one which has exactly twice the slope of this one. So I guess that this unit is designed to be connected to an indicator which uses a nonlinear scale. Actually, two different scales in order to optimize the accuracy from 0 to 270 degrees, something like that. A scale similar to the scale of this altimeter, and there is a second scale which is compressed. So I think we should have something similar. I did the complete reverse engineering of that device. You can see on the right here the power supply. This regulator delivers a voltage of plus 5 volts. There is here a watchdog circuit. The output of this 555 is connected to the reset line of the microprocessor. And there is here a circuit which delivers a high level at the output when the system is operational. On the left here we have 4 pairs of input voltages. In the middle here, pin 13, we have an AC voltage 400 Hz corresponding to the power supply of the magnesin transmitter. This circuit permits to compensate the voltages at 400 Hz which are present on the two outputs of the magnesin transducer. For that purpose, a voltage of 1/3 or 2/3 of these AC voltages are generated and are subtracted from the signals C and D here. It is the goal of these resistors here and these two op-amps. If you calculate, you find what is written here. This output corresponds to the input voltage present here, minus 2/3 of this AC voltage. And for the second output here, we have the input voltage, which is this one here, minus 1/3 of the AC voltage. And this permits to have mainly the second harmonic on these two outputs here. These two multiplexers permit to select one channel among 4 possible channels. The 400 Hz reference signal is also fed to this comparator. At the output, we have a square wave at 400 Hz. This signal is fed to this PLL. We can see that we have a divider by 4 in the feedback here. So therefore, at the output, we have a frequency of 1600 Hz. Here we have a frequency of 800 Hz. And of course here 400 Hz. The reference signals 400 Hz and 800 Hz are fed to this multiplexer. So therefore, at this output, we can have 400 Hz or 800 Hz if we have a correct setting of this multiplexer and this one also. So we can see here on the top an integrating ADC. The input of the ADC corresponds to the difference of these two voltages. This input, which is the input of this integrator, and the second input here, which is actually the common voltage. So we can see that this multiplexer permits to permute these two inputs. Therefore, it is possible to invert the polarity of this input here And we can see that this inversion depends on the state of this input A0. And A0 was this line here, which can be at 400 Hz or 800 Hz. Therefore, we have here a phase detector. If we suppose that A0 is at 800 Hz, we have a demodulation of an 800 Hz signal. This permits to convert the AC voltage at 800 Hz, which is the second harmonic of the magnesin, into a DC current which flows through this resistor. And this current is measured using this integrating ADC. Okay, we can see on this table a resume of the functioning of this ADC. So it is possible to measure the input voltage here, the opposite voltage. It is also possible to measure zero. And there is also another configuration when this one is connected to the ground. And here we have a connection to this voltage divider which is connected to this output. This configuration permits to discharge this capacitor, because we can see that we have here a negative feedback, because if we suppose that we have an increase of that voltage, this one will decrease. Therefore, when this line is connected to this point, this comparator is in that case in linear mode, and at this output there will be a voltage between 0 and 5 volts here. So therefore the input voltage will be very low here, a few millivolts, and this voltage is also present across this capacitor. So this permits to discharge this capacitor. It is therefore possible to measure the amplitude of the second harmonic signal which are present on the output of the magnesin transducer. But this ADC is also used for the generation of the output voltages. The method is interesting, so let's see how this thing works. We have here 4 identical circuits. Let's concentrate to this circuit only. So this circuit permits to generate at output number 6 DC voltage from 0 to 5 volts approximately. We can see we have here an integrator, but we have here a low leakage switch. This op-amp has also a very low input current here, approximately 1 picoamp. And here we have a polycarbonate capacitor. This line here is connected to the input multiplexer. Therefore, it is possible to measure exactly the voltage present on that line, which is also the output voltage. If we want to set a voltage at this output, this transistor turns on, and therefore it is possible to change the output voltage of this integrator by changing the state of that signal here, which is a digital signal, 0 or 5 volts. If we consider that the input voltage is 5 volts, which is actually the ground, the virtual ground, therefore there is no current flowing through this resistor because we have the same voltage here, but we have a positive DC current flowing through this resistor here. We have 5 volts across this resistor, so therefore a current of 50 microamps which flows through this transistor. Therefore there will be a decrease of the output of this integrator. Otherwise, when this line is at 0 volt, there is a current of 100 microamps flowing through that direction, but we still have a current of 50 microamps. So therefore, there is a sink current of 50 microamps flowing in that direction. So this permits to increase or to decrease the voltage as the output of this integrator. The code will measure from time to time the output voltage here, and depending on the sign of the difference between the actual voltage and the target voltage, this line will be set at high level or at low level in order to recover the correct voltage at this output here. When the voltage is correct, this transistor is disconnected, and therefore this integrator is in hold mode, and therefore the voltage is constant here. This op-amp doesn't work properly close to 0 at this output. This diode permits to have always a voltage above 0.6 and 0.7 volt at this output, and therefore this op-amp works in linear mode. So this is a DAC actually, which uses a digital feedback inside the code. We have also this circuit which permits to generate the virtual grounds, one at plus 5 volts, second one at 7.5 volts. There is also a 10 volts reference voltage. It is used also for the dual slope ADC. And the 10 volts is also present in one pin of the sub-D connector. That's all for today. Thank you for watching and see you next time for another video. Bye bye.